So we had seen system noise, okay, in the last class, and we had derived few equations, right, which is your noise power, and we had come out with some equations as well, right? And Tn is nothing but your noise temperature, the Boltzmann constant, okay? And we had even solved a problem as well, right? So moving on with our discussions, today we'll be looking into something which is called antenna noise, okay? Now, since these satellites are there out in the space, okay, we'll be having a lot of noise. When I say noise, it's not just due to the internals of the satellite, but also due to the space. Okay, so in space, you will have something called cosmic noise. Okay, and you will have something called solar noise. Okay, due to the sun. So all these actually contribute to inefficient communication from the TTNC center to the satellites. Okay. So antennas operating in receiving mode introduce noise into the satellite circuit. So which means these antennas are prone to the uh, loss. Okay. So loss is here in the form of noise. Okay. So we do not want any noise um, uh, to be associated along with our communication. So whereby what we will do is we will try and nullify this noise, okay? And before nullifying the noise, we should identify as to what noises are involved, which is hampering our communication system, right? So noise, therefore, will be introduced by satellite receiving antenna and the ground station. So this ground station is nothing but called your TTNC, okay? So this ground station is nothing but called your TTNC. So can someone tell me what is TTNC? Can you unmute and respond? We have seen these in our previous classes, right? TTNC. What is it? Telemetry, tracking, and command or control center, right? Okay. So the antenna noise can be classified into two. Okay, the one is the noise originating from antenna loss, and the other one is your sky noise or noise due to the external environment. And the first one is because of the internals, okay, just because of the antenna. Sky noise is the term used to describe microwave radiation which is present throughout the universe, which appears to originate from matter in any form at finite temperatures. Okay. So at different temperatures, okay, we see that there is a kind of noise that is generated, and that is nothing but called your sky noise. And these temperatures are very harsh. Okay, it can go minus 100, minus 150, and it can even go, you know, too high when it actually is, close to the sun, probably in, a few hundreds of degrees, right? So which means our systems are to be calibrated in such a way that, it can withstand both higher temperatures as well as extreme low temperatures. Okay. Then such radiation, in fact, covers a wider spectrum than just the microwave spectrum, right? So if you can see the graph over here, okay, you have frequency at one end, and the antenna noise, okay, it's actually in the temperature, okay, antenna noise temperature. So the noise is in the form of heat, okay, and it's measured in terms of kelvins, degree kelvins. So as the frequency of operation is less, okay, you can find that the the antenna noise is too high. So these are called as galactic noise region. Okay, so when the frequency is in the mid-range from 1 to 10 gigahertz, then it is called low noise region. Okay, because that's when it actually drastically drops from 10,000 to 100. Okay, somewhere in 100 to few uh, degree kelvins is manageable. Okay, and then as your frequency increases, okay, due to the water vapor, as I told you, the rain attenuation, okay, water vapor. So even because of that, and due to oxygen, because this is in a troposphere, okay, this is in troposphere, and it is termed as tropospheric noise region. So because in this region we find oxygen as well as water, which is H2O, okay, oxygen, and specifically when combined with hydrogen, two atoms of hydrogen, it combinedly forms the water. So this is an detectable noise temperature of an ideal ground-based antenna, okay, which is actually in the ground station. The antenna is assumed to have a very narrow beam without side lobes, okay, or electrical loss. So which means we are trying to consider an antenna which is very ideal. Okay, so below 1 gigahertz, the maximum values are for beam pointed at the galactic poles. At higher frequencies, the maximum values are for the beam just above the horizon and minimum values for zenith pointing. So as the distance or travel of signal changes, your losses or the temperature, okay, losses in the form of temperature also does vary. Okay, the low noise region is between 1 to 10 gigahertz and is the most amenable to application of special low noise amplifiers. So in this region, okay, we will actually design LNAs, okay, low noise amplifiers. So the equivalent noise temperature of the sky as seen by Earth station antenna is shown in this figure. Okay, so yeah, the lower graph is for antenna pointing directly overhead, while the upper graph is for antenna pointing just above the horizon. So these are two different antennas and how they respond based on how they are calibrated or where they are placed. The increased noise in the later case results from thermal radiation of the earth. Okay? So when the sun rays falls on the earth, the surface also gets heated up. Okay, the molecules get heated up, and there's a blanket of heat that surrounds earth. So this also results in a certain amount of noise contributed. The graphs show that at low frequency end of the spectrum, the noise decreases with increasing frequency. Yeah. So as the frequency increases, okay, the noise decreases. Any absorptive loss mechanism generates thermal noise. So anything that absorbs these loss is actually in the form of temperature. There being a direct connection between the loss and noise temperature. So which means as your loss increases, your temperature will also increase. Okay. So we can say that it's directly related, directly proportional, the noise and temperature. Rainfall introduces attenuation. So this is nothing but called your rain attenuation, right? Attenuation because of the rain, and this happens because of the water molecules. And therefore, it degrades transmissions in two ways. It attenuates the signal and it introduces noise. So it's not only just degrading the signal, but also it is introducing noise. So it's a double impact. Okay, it's not only just creating noise, but it's also affecting the signal, okay, in two ways, right? Satellite antennas are generally pointed towards the Earth, and therefore they receive full thermal radiation from it. As I told you, since there is a blanket of heat surrounding the Earth's surface due to the sun's rays, so this heat is radiated back to the satellite antennas, which are actually facing towards the Earth's surface. In this case, the equivalent noise temperature of antenna, excluding antenna loss, is approximately about 290 kelvins. Okay. Antenna uh, losses add to the noise received as radiation, and the total noise temperature is the sum of the equivalent noise temperatures of all these sources. Okay, so not only just the antenna loss, but we can also see noise because of radiations, okay, because of the thermal blankets. Okay, all this will actually yeah. So there's another graph here, okay, which talks about the antenna noise temperature as a function of elevation. So you have elevation for considering 1.8 meter antenna height. Okay. So this is some of the specifications given just for your reference. Of course, it's not going to be asked for all these details. Then you can just understand that as your antenna elevation angle increases, okay, the amount of noise also does decrease. Okay, so which means antenna elevation angle and your noise temperature are inversely proportional. Okay, they're inversely proportional. Now let's talk about the amplifier noise temperature. Okay, so sometimes we will be using these formulas with respect to solving problems. Okay. The noise representation of antenna and low noise amplifier LNA is actually shown in 12.4. Okay, so here you can see that your amplifier gain is denoted as G, and then your antenna's temperature, okay, T, and your gain of the amplifier here. Okay, if you have two amplifiers, then we denote it as G1 and G2. Okay, so we will see them what they are actually talking about. The available power gain of the amplifier is denoted as G. As we all know, gain is denoted as G. And the noise power output as PN0. Okay, noise power output. For the moment, we will work with noise power per unit bandwidth. So we are considering just a unit of bandwidth, but we are not considering the full one, which is simply noise energy in joules. Okay, right. The input noise energy coming from the antenna is, so much. So where this is your noise, okay, and not of antenna. Okay, P is your power and N is your noise. Right. The circuit used in finding equivalent noise temperature of A. Okay, so this one is actually put up here down, and B, two amplifiers in cascade. So this is a single amplifier, and you can find that these are cascaded. This is a very much important concept where many times it has appeared in your examinations, right? The output noise energy, N is noise, N naught will be Gn0, okay, Gn0, and plus the contribution made by the amplifier. Now all the amplifier noise, whenever it occurs in the amplifier, may be referred to as input in terms of equivalent input noise, because all these can be termed as input noise temperature. Okay, so your antenna's temperature. Okay, so ultimately it's a combination of many things. This allows the output noise to be written as noise output is equal to gain and then K you all know, T and plus TE. So TE is nothing but your noise temperature and the temperature of the antenna, T and. Okay. The total noise is referred to the input uh, is simply N naught out divided by G, or this is the formula that we will be using. Okay, K into T and plus TE. So your G goes out here, the gain. So instead of output, it is input. So output only, gain is calculated with respect to output alone. Okay, this can be obtained by the measurement, a typical value being in the range 35 to 100 degree Kelvin. So this is the normal range. Okay, it can, the lowest being 35 and the highest being 100. So typical values are given uh, in the previous section. Right. So ultimately now, since we have two amplifiers here, okay, G1 and G2, so the total gain will be G1 into G2, right? So the cascade connection, it's going to be G1, G2. So that's the total gain. And the noise energy of amplifier 2, okay, so that is given as K TE2, just to differentiate that this is just because of the second amplifier. And if I have one, if I have numeral 1 here, it is because of the first amplifier. So the noise, will have to add both the antenna's noise temperature and the total temperature just because of the first amplifier. Okay, so adding them all, okay, adding them all, the first and the second. Okay, so this is what we are going to get, which is T and plus TE1 plus K into TE2. Okay, so here what is TE? TE is nothing but the noise temperature of the amplifier. Okay, fine. So the noise energy may be referred to amplifier 1 input by dividing the available power gain of amplifier 1. So this noise, okay, that I am seeing with amplifier 1 can actually be taken with the noise of amplifier 2 and divided by gain 1. So it's one or more the same, right? Okay. So taking this into consideration, okay, with our previous formula here, okay, when we substitute, we are going to get this, which is 12.21. So the total system noise that we can think of is K into TS. So this is system noise, system temperature. Okay, system noise temperature. So in short, we can even call it as TS. Okay. So TS now is a combination of your antenna's temperature, okay, and your noise temperature, and the temperature due to the second amplifier and the gain of the first amplifier. Okay, so this is nothing but our noise, right? N naught 1. Okay, so all these noises are added, okay, because these are all a kind of noise. So you can see that these are all added. It's not minus. This is a very important result because it shows the noise temperature of the second stage is divided by the power gain of the first stage. Why? Because this gain is disturbed just because of the second amplifier, right? So whatever gain you get here, whatever gain that you get here in the first stage is disturbed just because of the noise in the second amplifier. So which means if you directly divide the gain, then the losses are easy to be calculated. Right. So therefore, in order to keep overall system noise as low as possible, uh, we actually use the first stage as LNA, okay, low noise amplifier, which means the range will be 1 to 10 gigahertz frequency. Should have higher power gain as well as low noise temperature. This results, so we get a generalized equation now. Okay, so T and plus TE1, TE2 plus divided by G1, and then if we have the next stage, okay, so it's going to become TE3, okay, divided by G1, G2, so which means the next stage is going to be TE4, G1, G2, G3 divided by G1, G2, G3, right, and so on. It just goes on, right? An alternative way, so this is just talking about the noise factor, okay? An alternative way of actually representing the amplifier noise is by means of the noise factor F. So F is nothing but your noise factor, the total, whatever noises that we have discussed so far. In defining the noise factor of an amplifier, the source is taken to be at room temperature, okay, denoted by T naught. T naught is ideal temperature. So whenever whatever calculations or experiments that we do, we normally refer to room temperature. And if we want it in the form of Kelvin, then it is going to be 290 kelvins. Okay. Now you can see the input noise, okay, wherein it has from source K T naught, and the output from the amplifier, okay, which means the noise from the amplifier we can come out with is your noise figure F, okay, G is gain, then K, and then T naught, right? So where T naught is your room temperature. G is available power gain of the amplifier as before, and F is the noise factor. Yes. Now we will see a simple relationship, okay, between the noise temperature and the noise factor. So which means between T and the noise factor F. Okay, so TE is the noise temperature, and F is your noise factor. Okay, that means T and, okay, the antenna's temperature will be taken as T naught, which means in the room temperature, since the same noise output must be available. So finally, you know, we come up with this equation where you see TE is equal to F minus 1, and this is the standard, okay, system loss into T naught. Okay, so if we want to represent it in the form of log, okay, then we use 10 log of F. So we can see that, you know, there's an equivalence between noise factor and noise temperature, right? So there's a direct equivalence here between the temperature and between the noise factor F. So if in the question it's asked to derive the relation between T and F, okay, you will be using this equation, which is 12.26, right? So here, you know, you can see that if you want to express it in the form of decibels, okay, then you'll be using 10 log and the value of F. So that's why you see this square bracket. Now remember, we had spoken about this in our initial classes that, you know, whichever values or the parameters, whenever it's given in the form of square bracket, okay, then we will be looking into its decibel format. Okay, right. So a small example is given here, okay, which talks about finding out the noise, okay, the input noise temperature. And LNA is connected to receiver, which has a noise figure of 12 dB. So directly I have the value of F to be 12. The gain of this LNA is about 40, which means my G is equal to 40. And the noise temperature, okay, is 120 Kelvin. So which means my TE, capital T, small e, is about 120 Kelvin. Calculate the overall noise temperature referred to the LNA. Now, as I've mentioned in the previous classes as well, okay, your formulas you can use based on the inputs that are given, okay, based on the values that are given. Okay, so 12 dB is a power ratio of 15.85 is to 1, and therefore, you know, if you want to convert this, right, so your TE2 is equal to F minus 1, okay, F minus 1 into your T naught, okay, so this we are using, right? So totally we are getting about 4,306 Kelvin. Then now we have to consider the gain, right? So the total temperature is going to be 120 plus this 4306 divided by 10 raised to 4. So totally we will be getting, because this 40 dB, okay, we are converting, it's a power ratio, okay, so we are converting it, and um, we actually divide it with the Kelvin, right, and we totally get about 120.43, so which means it will become 0.43 here, okay, 0.43, so that 43 is adding with 120, so it becomes 120.43. So these conversions is what that you have to take care, okay, you have to take care, right. In example, it will be seen that the decibel quantities must be converted. Now this is very important, okay, that's why I have mentioned here, okay, for your understanding, okay, this is very important, okay, you will have to remember these concepts, because if you do not remember, okay, to convert, you might directly put in those values and you will not get the proper values, even though your formula might be right, okay. So decibel quantities must be converted to power ratios, okay, power ratios and decibel quantities, keep this in mind. You'll have to just take it in the form of power. Also, even though the main receiver has a very high noise temperature, its effect is made negligible by the use of LNA, okay, right. So that's the importance of having the low noise amplifier. Now we will be discussing about the noise temperature of absorptive networks. Okay. So this noise is not just because of only the antennas, not only because of the cosmic noise, not only because of the solar rays, okay, but then it can also be because of few more factors, okay, the absorption ratios as well, which plays a very major role. So let's look into them one by one. An absorptive network is one which contains resistive elements, okay, which means it acts like a resistor. These introduce losses by absorbing energy from the signal and converting them to heat. So this is nothing but called your noise temperature, okay, noise in the form of heat. Okay, fine. Resistive attenuators, transmission lines, and waveguides are all examples of absorptive networks. And even rainfall, which absorbs energy from radio signals passing through it, can be considered as a form of noise. Okay, right. So all these are to be taken into consideration, and we have to look at it one by one. Because an absorptive network contains resistance, it generates noise. So now we will try to put that in the form of equations, and the power loss can be taken as L, okay, and your resistor, okay, the terminating resistor is taken as RT. Fine. The power loss is simply the ratio of input power to output power. So if I'm getting the same values at the input and the output, okay, then I do not have a loss. But if I'm giving a higher value and getting a lower value, then it means that there is a loss. So I can compare that when I put them in the form of fraction. So at the numerator, I will have the input power, and at the denominator, I will have the output power. Okay. So let the network be matched at both ends to a terminating resistor RT. At one end and an antenna at the other, okay, as shown as figure 12.5. So see this here, you have your radiating noise at one end, then I have my network which is lossy, and the power loss is L:1, and then you have my resistor, okay, the equivalent resistor, which is actually grounded, right. So the terminating resistor, the RT at one end of the antenna, and let the system be some ambient temperature Px, Okay, so let there be some ambient temperature, which means because of the environment. Okay, so we can probably take it as Tx. The noise energy transferred from RT into the network is K times Tx. Okay, so Tx is here, which is nothing but your ambient temperature. And then you have your RT here, okay, which is the terminating resistor. So if I multiply both of them, it becomes Tx and RT. Okay, K times Tx. So let the network noise be represented at the output terminals. The terminals connected to the antenna by an equivalent noise temperature, Tn noise temperature, okay, W0. So this is nothing but your network matched at both the ends. So I have my radiating noise, okay, and at one end I have the terminating resistor. So the noise energy radiated by the antenna, okay, N rad is nothing but K times Tx. Tx is nothing but your ambient temperature divided by system loss plus K into Tn W0. Right. So Tx we are very much aware of, which is because of the ambient temperature. Okay. The available noise energy which is spread into the antenna and radiated is K times Tx. Keep in mind that the antenna resistance to which the network is matched is fictitious. So which means, we are not very much sure as to how much we are going to match. But then it all happens with, trial and error process. But it does not generate noise power. This expression, so the final expression that we can get is, Tx into 1 minus 1 divided by L, which is nothing but your system loss. Okay, so when I take it common, and K is also taken out, so I get 1 by L. Okay, so this whole thing, right. This is equivalent noise temperature of the network referred to the output terminals of the network. The equivalent noise at the output can be transferred to the input on dividing the network with power gain. Okay, so loss, okay, the inverse of loss is nothing but your power gain. 1 by L is your system loss, and L is your system loss, and 1 by N becomes your gain, the opposite. Right. Thus, the equivalent noise temperature of the network is referred to the network input. Okay, so which means we'll be having the noise temperature, okay, which is as shown as in 12.30. Okay, so based on your equations, okay, we can actually, based on your values that are given in the problem, we can use these formulas and accordingly employ them, substitute, and calculate. So as I was mentioning, with respect to the formula, okay, so those values that you get in the question, you can extract them and you can try and substitute them here so that it becomes easy for you to analyze it. Okay, since the network is bilateral, okay, we need to apply, so which means equations 29 and 30. So this equation, and we'll be using 1 minus 1 by L. So these two equations apply for signal flow in either direction. Thus equation 30 gives the equivalent noise temperature of a lossy network referred to the input of the antenna where the antenna is used in the receiving mode. So ultimately we have to find out, or we have to take care that all the system losses are taken into consideration. If the lossy network should happen to be at room temperature, okay, so which is about 290 Kelvin, okay, then Tx is T0, then a comparison, then we can find that your noise factor is actually equal to the system loss, which is L. This shows that your room temperature, okay, at room temperature, the noise factor of a lossy network is equal to its power loss or system loss. So only if it's in room temperature. Now keep in mind this condition is to be satisfied. Okay. So the next that we will be looking into is the overall system noise temperature. Okay. So we have seen the antenna's temperature. Okay, the LNA is used instead of just having the amplifier. Okay, we will use a low noise amplifier and the gain is G1, and the temperature noise is TE1 for this amplifier. And this will be at your receiving noise factor. Okay, now not only that, even the cable is associated with the loss. Okay, because as the cable increases, okay, if the length of your cable is high, then the loss is increased. So as much as possible, we try to get sufficient amount of cable connecting the low noise amplifier and the receiver uh, section. Right. So connections are used in examples illustrating the overall noise temperature of a system. Okay, so here I give my input cable loss. LNA can be moved a little towards the receiver so as to reduce this cable loss here. Okay, and increase the cable over the left hand side. Right. So the figure showed a typical receiving system applying results of previous sections. Okay, so your uh, system temperature, okay, in the form of noise is nothing but your antenna's noise, and then the noise temperature TE1, okay, and L minus 1 T naught divided by G1 plus L into your factor of noise, okay, F minus 1 into T naught divided by G1. Okay, so loss due to system and loss due to noise, or these two are taken. The significance of individual terms is illustrated. Okay, so we will see an example and you can understand as to how we extract data and contribute to the formula. For the system shown in figure 12.6a, okay, so we are talking about this figure here. Okay, so with that figure, we are referring to the problem. The receiver noise figure is 12 dB. Okay, so you will have 12 dB. So this value can be directly taken, right? And it can be substituted. Then cable loss is 5 dB. LNA, okay, low noise amplifier gain, which is G1, can be taken as 50, and its noise temperature, that is TE, is 150. Okay, and the antenna noise temperatures is about 35. Calculate the noise temperature. Whenever there is this kind of noise temperature, okay, from noise temperature to power conversions, then you'll have to do this conversion. Okay, so 10 raised to 1.2, which is about 15.85. Okay, so you'll have to take this, okay, 12 and put it to the power of 10 with a decimal. Okay, so now for cable length, okay, so it was about cable loss is about 0.5, right? 5. So always keep in mind you divide by 10. Okay, so it becomes 0.5 and put that to the power of 10. So to the power of 10, 0.5, so I'm converting it, and here I have 50 divided by 10, it becomes 5, and then 10 raised to 5. Okay, so we try to substitute all of these values into our formula, and we end up getting the value as 185 Kelvin. The most repeated question actually you can find in your examinations. Right. So now again, let us repeat the same example, okay, with the application of a different value, and we will see, okay, what can happen. So if we try to rearrange them, okay, as I told you, in A and B, we have done some rearrangements. Okay? So we push the LNA this side, we reduce the cable loss here, okay, which is something between your amplifier and your receiver section. And we brought it towards the left hand side. So these are two arrangements. This was the original one, and then we arranged it in the form of B, right? And then we will again calculate for this arrangement. So in this case, the cable precedes the LNA, and therefore what is happening, whatever loss is there, that is getting amplified. Okay. So here what had happened, the loss is after the amplification, but here the loss is before amplification. So which means the loss is also getting amplified. So which means, should we consider this arrangement in B or should we consider the arrangement in A? Which arrangement is good? Yeah. Which arrangement is good? The one in A or B? Can you unmute and respond? Yes. Is it A or B?
Sir, B.
Why is it B, Pranay? Why do you think so it's B?
Sir, cable loss is
Yeah, go on. Go on. Anybody else wants to take it? Jitendra? Jitendra, you want to take it? Which arrangement is better, A or B? Okay. So as we see in the figure here, okay, the noise or the loss, which is after the amplification, is better. Okay. If not, the loss, if we put in the initial state, okay, then even the loss is also amplified. So which means loss becomes higher. So let us see this in the example, and you will be able to understand it in a much better way. Okay. So TS is equal to 35 plus 3.16 minus 1, just a substitution. Okay. And then you can see that, okay, the loss is about 1136 Kelvin. But in the previous one, okay, it had just about 185. So which means the arrangement in A is much, much better. So the important point that you have to make note is that the LNA must be placed ahead of cable. Okay, so this is important. So if this isn't followed, okay, then the losses are mounted because of the amplification that happens. Okay, so I think students, we will stop here. Okay, and we will see in the next class as to how this carrier to noise ratio is taken into consideration. Okay, we will see few examples, few problems. Okay, and we'll try and understand these concepts with respect to your CNR, carrier to noise ratio.